So, hi everybody, welcome to today's lecture on deep learning, finally. I think I've hinted before on these methods in previous lectures, so today we're going to talk about them. There's been quite a few. Can you really see this guy? Oh. Where's the big laser pointer? Is that here?
The what?
The big laser pointer?
Oh, I can find it.
Oh, thank you. I think I'm getting low on battery. So the deep learning has had quite some coverage in like social media and basically all over the web and news. And it's always emphasized as this big, great new method, right? Like deep learning, the new revolution in machine learning. But what we're going to see today is it's actually not new at all. It's based on the perceptron that we talked about in the support vector machine lecture way at the beginning of the course. So the basic techniques were invented in the 50s and 60s. But then in 2006, around 2006, something happened. And that made them really shine and work. Since then, they've been ever increasing in popularity. So today I'm going to talk about the why. So why should you care about deep learning and want to learn it? What is it, and how do you actually do it? So why do we care about deep learning? So first of all, it works. So we used to joke in computer vision conferences, even in the big ones like CVPR, that computer vision is about finding the images that your algorithm works with. And there was a sad, sad minor truth in that, as there are like 4 or 5 big image databases which were used for benchmarking, and you would evaluate all of those, and then if 3 worked, you were pretty happy, and those were the ones that made it into the paper for a lot of authors. So this was kind of the thing, how machine learning, especially in computer vision, actually was the state of the art. And nowadays, Google, Facebook, Twitter, Microsoft, all the big companies are starting to use these deep learning methods, and they work really, really well. The other option is it's actually really fun. You have this notion of building a brain, kind of, because they're modeled after these perceptrons, and we talked about that they're kind of a model for neurons, right? So it's really exciting to work with them. And the other part is, if you have a random forest, especially, it's off the shelf. There's not much you can tweak. There's the number of trees, there's the number of random splits, right? But in the end, it's just this one line of code, nothing more to think about. With the deep learning methods, you build these elaborate networks, and this also means you have to know a bit more about what you're doing, but then you can really have fun. You can like resize layers, see about the influence of that. You can change the optimization routine. So if you're interested in doing research in this area, although you might think, well, this has been around for a long, long time, it's actually the case that you still can contribute a lot, even on levels that do not require you to go through 2 years of complicated math. So Google Trends, if you look for deep learning, shows a really, really clear incline here in the recent years. So this is the Google Brain happened in 2012, where they built this big, big network. And since then, people have gotten more and more interested. But if we contrast that to support vector machines, you see there still is a lot of interest in the methods we covered earlier in the course. And I'm going to also talk a bit about why that is and why that also, I think, should still be. But you see the support vector machine is coming down, and deep learning is going up. So as I said, this was a big breakthrough. Like we had this example in one of the very first lectures. I think Hans-Peter showed it for the k-nearest neighbors. And just to remind you, this was the C-Sail demo, and Hans-Peter even just took a picture of this room, of this audience room, uploaded it live in the lecture, and showed the result. Nobody would have dared that 20 years ago. So this is a big thing, because they not only have the system online here, right? So this is, you can click on one of the pictures, and it shows you, let me get rid of this. It shows you the scene prediction, right? It's computing. Oh. It's computing, and it's showing you what kind of scene this is. Oh, I don't have network connection at the moment. And it worked really well. It even said for Hans-Peter's picture, this is an auditorium, which is exactly right. So they must have a lot of confidence in the system to allow users to upload even pictures they've never seen before. And to be frankly honest, CVPR got quite boring because of this. I think Hans-Peter gave that comment to me. After the last conference, he was like, it's pretty boring. 95% of everything is convolutional neural networks. So the whole field at the moment is converging to these deep learning methods. And this is the Google Brain project in 2012. So they were the first ones, I believe, to do this in a really gigantic framework. So they took a whole cluster with 16,000 cores to train one gigantic network. And they trained this unsupervised because for such a large network, you need a lot of training data. So their sample sizes were in the millions. And where do you get training data if you need images? They trained it on images. Images that preferably all have the same size. Where would you go? Data scientists. Where would you go? You need something that is free on the web. You can download tons of images. It's not that hard. Flickr, for example. And now Flickr, I think, doesn't assure you that they're all the same size. So it does? No. Oh, no. So they went to YouTube. They used YouTube thumbnail images. All the same size, millions over millions of them, and everyday fresh ones. And they trained for 3 days. And then people made all these jokes because then they could have asked for the meaning of life, right? This is a brain. They call this a Google brain. And what it found was a cat. So they looked afterwards in this network what single neurons correspond to. I think there's been biology research actually in this, that we do have single brain regions that fire for familiar faces. And they looked into those single kind of neurons inside the network and looked which response, like which input would get this neuron to fire really strongly. And they found a cat neuron and a face neuron. And this makes sense because a lot of YouTube videos actually are about cats. So this machine has seen lots of cats. So this is another project then. So that was 2012. And then in 2015, Google DeepMind published a Nature paper that can play, they designed a big network for reinforcement learning that can play Atari games. So this is now Breakout, where you have this big field of blocks at the top, and then you kind of balance this ball and like try to not let the ball escape. And this network didn't know anything about that game. All it was given to was the visual input and the score that it achieves. You can see here in the beginning, there's a lot of randomness going on because there's not been much training. There's no feedback. Everything is random. It's just randomly pushing buttons, trying to see what happens, kind of like a toddler would do. But sometimes it lands a hit, right? So the score went up. So it's learning that there are certain actions that make the score go up higher. And you can see after a couple of minutes of training, or was that an hour? 2 hours. After 2 hours of training, it's starting to play like an expert. So it's catching the ball now pretty reliably. But then something really cool happens. So 2 hours more. And it learned that if it digs a tunnel and gets the ball up there, right? This is how we play Breakout. You try to dig this tunnel and get the ball up, because then you can just sit back and relax and wait for your points to pile up. So does this network do this the way a human does it? So does it reason, hey, if I really would dig a tunnel through, then the ball would stay up there and I wouldn't have to like hectically change the position of that bar down there all the time. And the answer is no, it can't do that. It can't reason. What it does is, just by random chance, if you train long enough, this happens by accident, right, somewhere along the line. And the network gets this big reward. The score goes up really, really high. So what it's learning is, if I do this, then I get a really high score. But for that to learn, it needs an example of it. So it can only learn things, there's the restriction. It can only learn things that it encountered. And for example, they said one limitation of this network is Pac-Man. Pac-Man is incredibly hard, because at the beginning, you push the buttons, and there is not even a score going up. Like, you basically have to push a long sequence of buttons, and you actually have to do planning to play Pac-Man. So it's harder to encounter random solvings of mazes than this. So this is more from a field that we actually haven't really touched on. This is called reinforcement learning. So reinforcement learning is all about these playing game strategies that involve a certain amount of planning, where you have a reward at the very end of the game, right? In this case, you actually had a score going up, but you can also do the classical reinforcement learning. You can shoot onto a goal, right? You have a couple of sequence actions, and at the end, you get a reward. I've won the tic-tac-toe game, for example, or the chess game. And then one of the big problems is to assign credit. Which of the moves you did, if it was a whole chess game, which of the moves you did actually ended up in you winning the game. So, but this also, deep learning behind it, like teaching computers to play games has also been around for decades. But this was mind-breaking, like that, mind-boggling that they actually got to this level. So what's the difference? We have seen machine learning methods in this course, support vector machines, decision trees, boosting, random forests. And in all of these methods, we needed to hand design the input. Remember, we talked about this in the beginning, the apples and oranges a lot, that if you go by weight or shape, your classifier is lost because the actual signal that separates the classes is not in there. So you have to come up with this idea to actually measure the color, to have the classes separate. And then, but once you have these features designed, you would train your support vector machine, your random forest, or something to get this decision boundary. So far, so in the old days, you would also come up with a decision boundary. Now, with all the machine learning methods we had so far in this class, you design the features, then the algorithm gives you the decision boundary. And with these deep learning methods, we go even one step further. So what does this look like for image processing? So this is a manual filter bank. This you would use with a random forest or support vector machine. You have an input image, and these filters here just look for different frequencies inside the image. You can kind of think that this, for example, would fire on a nose, right? It's like bright in the middle and darker on the side. A nose is bright in the middle and darker on the side. So you could make them very specifically tailored towards the task, or you could just have more general filter banks that people designed. Now, in deep learning, all these filters here are initialized randomly. And these features are actually extracted from the data. So the machine only sees these face images, and it should classify whether that picture shows a face, yes or no. So in the beginning, you have your normal training set, right, where you actually know the answer, and you feed that into the network. But the big difference is that you didn't tell it to look for these type of edges in the image. It's optimizing over those features as well, figuring them out and figuring out what it has to look at in order to classify this as a face or not. And this is also not really working. And one thing then people discovered and that they really liked was that these here are low-level features. These are edge detectors. Something that is bright on one side and dark on the other side, here like an eyebrow maybe. But you already see here, as I said, this is an eyebrow, kind of. So you have higher level features now. You already have features there that give you a clue the machine is actually learning to detect faces. It's looking for parts of faces. And then in the next layer, you have really high features where it already assembled these to look into faces. So that is the one big advantage of deep learning methods. We don't have this manual feature design anymore because, yeah?
Is the idea that the medium level features are like linear combinations of low level features?
Yes,
Totally
kind of. No, they should be combinations of the lower level features. You're going to see more. Oh, the question was, is the idea that the higher level features are combinations of the lower level features? They're not strictly linear combinations, but they are combinations.
Yeah, because there's probably a resizing.
Yeah. So this is the one big change, because the other part, the hand design, is really frustrating. I've been there during my PhD. Like, you can see it, especially in image processing. You can see the membrane, you can see the vesicles, and you just can't find the feature that discriminates the two. It's like not realizing, being blind and not realizing that you need the color feature to separate the apples and the oranges. And the deep learning methods get rid of that problem. You just put the whole image patch in, and it should figure it out by itself. Of course, if you have this apple-oranges problem, you still need to figure out what to measure. But in image processing, because we look at that image patch, we know the signal is in there, right? So it's up to the network to learn how to extract it. The other big thing that is different with deep learning method is they scale with the amount of data. And I find this curve very interesting because this explains part of the success that is coming now. So most machine learning algorithms, we talked about scale to a certain degree when your data set gets larger. And then at some point, you don't gain that much anymore for more training data. Do you have an idea why that is? Yeah?
That's because we predetermined the amount of features we're using.
Yes, so one part is we predetermined the amount of features that we were using, and we are also determining something else, typically when we have our classifier. Remember this bias-variance trade-off that we had? So there's only so much variance the classifier has, and most classifiers we talked about actually are trying to battle the overfitting, which means they're trying to reduce the variance. Right? But you need variance to actually fit data. What can happen is, let's make a more extreme example. Let's say I even only have a linear classifier. So my decision boundary is just a separating hyperplane. And I have a two-dimensional case, and I have two nicely behaved classes. So, and I just learn this line. And now, they're actually not that nice behaved. If I have a small amount of data, this linear classifier does the right thing. It doesn't pay attention much to this single data point because most probably it's an outlier. But what if I get millions and millions and millions more of data points, and I end up really filling this space, and really filling this space, and filling this space? Now it looks like it's actually a bad idea to ignore that outlier in the beginning, right? Because it's not that much of an outlier. But my linear classifier cannot go there, right? It's just a straight line. There's no way I can bend it to model this amount of data. So the deep learning methods have a lot of degrees of freedom. High variance, high variance, they can capture that. But there's also the drawback. This is the reason they need tons and tons and tons of training data. Because if I have high variance, what was my problem always? The training error goes down, and what does my validation error do? Yes, that was the right movement. It goes up, right? That was the problem of overfitting. Like my training error can go down, but at some point I start to overfit, and my validation error went up again. And another method to battle this overfitting is to try to actually really fill your space. So deep learning methods have a high variance, but then they need a lot of training data to battle overfitting. So as I said before, nothing is new here. Artificial neural networks are around since the 60s. Convolutional neural networks came somewhere in the 80s. And I'm going to briefly touch on recurrent neural networks because they're gaining in popularity now. And also this model was introduced in the 80s. So what changed? We just said the amount of data changed. And I want to show this video.
Sure. So I think maybe 5, 6, 7 years ago, when a bunch of us were starting on this, we used to explain deep learning as saying that it's a neural network, kind of simulates the brain. One of the problems with that analogy is it has led to an excessive amount of hype. With people thinking about super intelligences, similar to human brain. And of course, all of us that work in deep learning just know that's not true. And Mike Jordan likes to say that deep learning algorithms are really a cartoon of the brain, and then I think that's accurate. So, we see it trying to lay audiences and trying out the new analogies. So you can't tell people, don't think of it as not a brain, that's not helpful. So now when I think about building deep learning products, I think of building a rocket ship. So what is a rocket? What is a space shuttle or like a Titan rocket? It's a giant engine and there's a lot of fuel. That's basically what a rocket is. So I think of deep learning as being something similar. We need a giant engine. That's the giant neural networks we built, the big iron that can absorb huge amounts of data. And the data is a rocket fuel. And so I think because of a lot of computer systems work, we're now able to build these giant machines, giant engines, and because of the digitalization of a society and other tactics, we now have huge amounts of data, and it's a combination of these two things that lets us launch more and more rockets and have them go further and further.
All right.
So I actually didn't introduce him. That was Andrew Ng, from Stanford, and he was one of the guys behind this Google Brain project. So he makes 2 points here. One, I wanted to have in the beginning again, just to iterate this whole hype and that these neural networks are like brain structure. You already know that perceptrons really just are a separating hyperplane, right? In a very crude abstract model of a neuron. So this is what he's iterating here again, and this is what he means by a cartoon of a brain. What's the second point he makes? Why does he think these rocket spaceships are a good analogy for neural networks? Yeah?
Because they emphasize the two kinds of inputs you require for neural networks to function. So you need large amounts of rocket fuel data, and you also need the infrastructure, so the computing power.
Yes. Yes. So he's emphasizing these two parts of the rocket ship, right? The big engine and the big amount of fuel you need. And he's emphasizing this because these are the two driving things behind neural networks. You need large amounts of computational power, and you need large amounts of training data. And this is something that changed very drastically, if you think about it, between even the 80s and now. I mean, I made it even bigger here in contrast. That is the Mark I perceptron on the left. That is one network encoded in hardware, right? They actually built that. The wires in there are the single connections. On the right side is the cluster for the Google Brain, 16,000 cores. Right? There are worlds between those two. But it's the same model. It's really the same model. They're doing the same computation. And the other thing that changed is data size. I don't know if you remember that video that I showed of this poor guy sitting there all day long taking photographs, like literally paper photographs, putting them under a photo detector, pushing a button, saying right or wrong, and whether that is a man or a woman. Now, we just said these networks need millions of examples. And they couldn't even do it in parallel because this network only had one detector. So someone was sitting there day and night, putting under picture, under picture, under picture. And now we just go to YouTube, and we have 1 million training samples scraped in, I don't know, a day maybe. So, but you might want to do some deep learning. I do deep learning. And we don't have a cluster, right? We don't have the 16,000 cores. There is Harvard Odyssey. It's a good big cluster and infrastructure. But the good news is this is actually an advertisement from NVIDIA GPUs. So if you want to do deep learning, you really have to go into GPU computing. Like, I've met people who've done it on MATLAB, on CPUs, and you wait for months until your network is trained. And then you fiddle around with the parameters, hit go again, and again go on vacation for 3 months. So this reduces the training time to like 1 or 2 days. But this is also the reason I said I discourage people from using deep learning in the final projects. It takes time, a lot of training time. And on the final projects, you're on a time schedule. So I would advise against them, but only for this reason. So now that we're all motivated to get our GPUs to good use, what actually is deep learning? So I've already said multiple times now, we started with a perceptron. So I'm going to do a very brief recap of that, just so that you remember we have our very crude abstract model of a neuron, right? You have the input coming in. The x's there are our input, x1, x2, x3. Then you have weights, w1, w2, and w3. And what happens is the input comes in, and then x1 is multiplied by w1, x2 by w2. You sum them all up. You decide, based on that sum, whether that neuron fires or not. And then you have your output signal. So, and this, in the end, boils down to this very simple equation. You have your weights multiplied by your input x, right, the dot product. And then you have a bias b, and you can see in that model, if you want to, you can actually put that bias b into your w even. So there's just one matrix multiplication. And then this s is your step function. That was the decision whether you fire or not. And we said that this is just modeling a separating hyperplane. Your w is the orientation of that hyperplane, and your bias is shifting that hyperplane around. So this is really all there is to it. And the decision function, the step function, is not very well behaved, like mathematically, derivatives and everything gets tricky. So what we do is we model it with the sigmoid. And then we went on in that support vector machine lecture and talked about the XOR problem. And it's a big, big problem for the perceptron because it can't solve it. You can't solve the XOR problem with just one linear separating hyperplane, not in 2D. And we went on from there and talked about the kernel, right? We just took those points, put them into a higher dimensional space, and showed that then often they become linearly separable. So I hope you remember that. We're all on the same page now, because now I'm going to show you how to solve this XOR problem without this kernel trick, but with multiple perceptrons. So what you do is, this is one perceptron, just my one separating hyperplane, no bias here. I'm just putting them all through the origin. And now we take 3. Not just one, but 3 of these units. That's nothing more. I have 3 separate hyperplanes. So I can put those together into a matrix. So what I'm doing is W1 is described by W11 and W12, right? And I just put those weights into a matrix. And then the dot product can just tell me, is this to the left or to the right of this one hyperplane? This is how classification worked. So let's go back to our XOR problem. I now labeled the points A, B, C, D. And what I'm doing now is I'm using 2 hyperplanes. So what I can see now, B is to the right of both planes. Oh, I started with A. A is to the right of W1 and to the left of W2. So what I'm encoding up there, maybe the battery has recovered. What I'm encoding up here is plus means to the right and left means to the left. Minus means to the left. So A is to the right of W1 and to the left of W2. Kind of. Or under. And I can do that for the others as well, right? B is to the right of both hyperplanes. C is to the left of both. And D is in the middle again. So all I've done here is I've used multiple hyperplanes. I've solved this dot product, and I'm just describing these points now in terms on how they relate to the hyperplanes. And now comes the trick. Now I'm putting them into this coordinate system. And you can see A and D have the same description in this coordinate system. They're both plus minus. So they end up in the same spot here, plus, minus. B is plus, plus, so went up there, and C is minus, minus, so it's down there. So what did I do to my problem? I made it linearly separable. And I didn't do the kernel trick, but in a way, I introduced a new coordinate system, right? And in this new coordinate system, they are separable, and my perceptron can achieve the classification. And this is exactly what is there to deep learning. The perceptron we talked about before is shallow. There's only one separating hyperplane. What I did now is not only took I two of those in the first layer, I introduced a second layer. In the first layer, basically learned the description of these points that made them separable, and the second layer is classifying them. Does that make sense? Yes?
So this basis is in terms of those, that description plus, plus, minus, plus.
Yes, yes. It's so the basis is in terms of this plus minus. It's a very crude illustration of a new coordinate system. This is the point I wanted to come across. So this is what we're really doing. We have this input layer now. And then in the next layer, the first hidden layer, those are these multiple perceptrons. That are the lines in the beginning where I used 2. These are learning this new embedding of the data points. And then in the output layer, I have this last hyperplane that actually does the classification. Do you have other questions about this? Understanding this, what is happening to your coordinate system, that is all what deep learning is about. Regardless of the model you use, this is the trick that is making them work. So, and then if you multiply this up, it actually all boils down to matrix multiplications. The math behind deep learning is really not complicated. So you just have this dot product that we have before, and you have this step function, right? The sigmoid or whatever activation function you use. So this part here gets you from this layer up, right? My input X is down here. I have my weight matrix and my bias. So I'm here, and then this S decides whether these units here fire or not. So after evaluating this S here, I have values here. In the slides before, I only used plus or minus, but in real life, you actually have values here, how strongly they fire. And then you just do the same thing all over again. Just because this network here is not very deep, this is already our last layer. And you can see it's the same math here. It's just this is now the input for the next layer. You again have your W and your bias, but now there's G. And the reason this is G and not S is for the very last layer, you need to do classification. So if you have 2 classes, you just do the logistic function. If you have multiple classes, you use softmax, which just means you ensure that everything sums up to 1, right? Because in most scenarios, a pixel should only be one object, for example. And this is then this feature representation that comes with this. Because what you need to realize is this here, this patch, is nothing else than a W reshaped. That's actually really fun. That is also fun to visualize for support vector machines. That W, that gives you the orientation of your hyperplane. If that is trained on image data and you just reshape it to the shape of this input patch, you often can see patterns. So this is just a reshaped W here. And you can see this is what the filter, so it's a filter, it's a learned feature. We are updating these W's during training, and this is what comes out. So let's talk about what this Google Brain thing was. We can totally understand this now completely. This was an autoencoder. I said it was trained unsupervised, but it really is nothing more than a multi-layer perceptron, which is what we just talked about, where the output size has the same size as the input. What I just showed you was classification, right? Face, no face. Input was a whole image patch, and output was a classification, yes, no. What we're now doing is we're using an input layer, and then the output layer has the same size. And this network does not get labeled. That was the big trick they did, because it's hard to get 10 million labeled images. That means someone had to sit down, most probably even, and say face, not face, cat, dog, right? So this is easier because you don't actually need labels on the images. All you do is you have this input here, and you train the network to reconstruct this image. So that sounds silly, having a network that just gives the output that it just saw, right? So there's a trick to it. And the trick is we're reducing the size of this layer. So the network has to learn a representation of this image patch that is smaller than the actual image patch, but still captures as much of the signal of the image as possible. It's compression. And if you do this in a very boring fashion, without a sigmoid and without tight weights and all of that, all you're learning is basically PCA, right? We had PCA. So, but you can, for example, tie these weights. And people do that because it simplifies training and also leads to more interesting results. So what we're also restricting here is we're saying the W that does the encoding also should do the decoding. I'm tying those weights. I'm saying the W needs to be the same. That is often done in autoencoders. The other thing you can do is, people use this for pre-training, which we're going to talk about later. You can make this layer here actually larger than the input image patch. And the reason you might want to do this is this feature extraction idea. You might just use this network to learn features, and afterwards you could even train a support vector machine with those features. Maybe you want more features than you actually had input variables. But now you need to prevent the network from just reproducing the input by learning it by heart. So what people do is they add noise. What you train the autoencoder then with, it's called a denoising autoencoder, because all you do is you blur this image or add salt and pepper noise, but you know what the original version was. So you put it into the autoencoder, you get the reconstruction, and you give feedback for the training based on the reconstruction and the original image without the noise. That's the idea behind an autoencoder. And that's all what the Google Brain was. They let it run loose on all these YouTube images, and then they looked into one of these internal neurons, and that learned this cat representation. So the network had no notion of even for how many objects it was looking for. That is why this cat was so impressive. Right? It really only learned to reconstruct what it has seen. And you can make these architectures deep. Of course, it's deep learning. So what you do is you can see here, this is now the deeper structure for an autoencoder. And typically, the layers get smaller. If you do denoising autoencoders, they might all have the same size. But what you see is the weights are again tied. So this input weight here, W1, is the same as the weight up here. So you can tie these weights. And the reason people do this is that by learning something about the images, this seems silly, right? Like I saw this for the first time. I was like, there are no labels here. There's nothing guiding this network what it should look for, right? What I'm basically saying here, just show it pictures of cats and dogs, and hopefully it's going to learn something, features that actually also can discriminate between cats and dogs. But this network does not know that the task is to actually discriminate between the two classes. All it learns are descriptions of the data it's seen. But it turns out that often these are closely related. So I'm going to go now to the convolutional neural networks. This was a full perceptron-based network. I'm going to go to the convolutional ones next. Are there any questions about the autoencoders or multi-layer perceptrons? Yes?
So you tied neural networks to PCA just now.
Yeah.
That's actually something that I was kind of thinking about. If you were to use infinitely many layers, would like the final layer approach something like an eigenvector, or something like? How would you relate the eigenvectors of like the data set to the features that you're finding?
How would you relate the eigenvectors? So you have, the question is, if this would just learn PCA, how would I relate the eigenvectors that PCA would give me to what the autoencoder learns? Is that the question?
Not necessarily the autoencoder, but just like neural networks in general.
Sorry? Neural networks in general.
Yeah, exactly.
So in general, neural networks are not going to learn an embedding in that sense. And actually, the autoencoders, people mention that. These are the reasons they tie the weights. It actually also makes optimization better, but also this nonlinearity is typically used to learn manifolds that are not just PCA, but hopefully something better. But if you would learn PCA, then basically this W, right? I showed these filters here, this W reshaped. So those also would be your principal components. That's where they would be. What?
I think the nonlinearity.
Yeah, the nonlinearity is the difference in the tide weights. So other questions about just multilayer perceptrons? Yes? Okay, very good question. If I understood it correctly, it's about how to find these very first hyperplanes in the beginning. I showed that these now give you an embedding of the data that describes this coordinate system, and this makes it linearly separable, right? That's all nice that it works, but how do you come up with these two in the beginning? So what you do is you play Mikado. You do this in real life. You initialize the W's randomly and all the biases to 0. This is also why you often center your data around the origin by subtracting the mean. This means you know that all your data is kind of clustered around here, right? And all your hyperplanes go through the origin because you initialize the biases with 0. And then you do the W's themselves, you do randomly in the hope that they're going to cover the whole space. And then you start training. And during training, these guys now are going to shift and move. So this is part of the training. This is why they have so many degrees of freedom. So you would not try to fix them like I did here. Instead, you would start with this configuration. And by getting this feedback signal that this was not a good embedding, these hyperplanes would start to shift around during training to make the error go down. This is the way it happens. A very, very good question. Okay, let's move on to convolutional neural networks. So from multilayer perceptrons to convolutional networks. The multilayer perceptrons we talked so far about, I always had this input X, right? And if this input is an image, for example, all we did was we took the image patch and flattened it into one long vector and fed it into the network. This just calling flatten is destroying a lot of neighborhood information in the images. And if you think about it, I could even scramble the pixels around. As long as I use the same permutation for all inputs, the network would be totally fine. Right? There is no notion that there is a correlation or some kind of relationship between adjacent pixels in a multilayer perceptron. So convolutional neural networks address this and have this notion that things that are neighbored have signal to it. And you have a lot of applications where this is the case. The biggest one is image processing. So convolutional neural networks are typically the model of choice for image processing. They've also been used in speech recognition, for example. You have the same, right? Our voice does not just jump up and down randomly. We have these melodic patterns, for example, when we speak. So convolutional neural networks now look at this neighborhood. How does that work? It's really hard to find good visualizations, and I can't really think of one that explains it even better than this one. This is the best I found. This is an image of Einstein, right? And it's a quite large image, and it's capturing his whole head. So if I do a fully connected network, what I would do is, I said I unravel the whole image, right, with all of its pixels. So in that sense, I have then a weight from each single input pixel, right, to my next layer in my multi-layer perceptron. This is the way fully connected networks work. And this is not only not looking at neighborhoods, this is also a bit wasteful because, for example, we saw these intermediate representations that networks can learn. So if it would learn to look for an eye, right, an eye filter would only be this size, and all the rest would be useless, so it would have to be 0, right? Because I'm looking for something in the image that is similar to my filter. And the eye is capturing such a small part of this. So what looks to be quite more efficient is to have smaller filters and then shift this filter across the whole image and look for features that are similar to this filter. And this is a convolution. This is what convolutional networks do. Instead of connecting the whole image patch, they use these smaller filters, glide them over the image, and look for these features. This is the reason those filters I showed you, where they had these edge detectors and then noses and eyes, those actually came from a convolutional network. It's learning these smaller features that are convolved over the image. So this is a convolution here, just illustrated. So I have my smaller filter and I have my larger input patch. What I do is I put the smaller filter in the upper left corner, and then you basically just do a dot product, right? So in this case, the ones that overlap, here's the kernel, 1, 0, 1, 0, 1, 0, 1, 0, 1. And I just multiply 1 with 1, that gives me 1. 1 with 0 gives me 0, right? And then I sum up over all the fields. And with that, I can fill the square on the right. So a few things to notice is these numbers are higher if the image is more similar to the kernel that I used in the convolution. And the other thing to notice is this is slightly smaller because I can only compute convolutions where I can actually fit this kernel into my image, right? So I'm losing a bit at the boundary. So this is then the whole architecture of a convolutional network. You have an input. In this case, it's one of our famous handwritten digits. It's a 3, right? So now you have these smaller filters, and we shift them over this image. And you record the answer for each shift. So we're basically computing this red square here. And this gives you the convolutional output, 1 for each filter. And then comes the next stage, and that is subsampling. That is also something that is typically not done in fully connected images. What it does is it takes this convolutional feature map here and just takes every second pixel. That would be the boring case. What people typically do is called max pooling. They take a 2x2 neighborhood, and you take the maximum response of this 2x2 neighborhood. And there's something very neat about doing that. It's introducing a certain amount of translation invariance to your classifier. Because if you think about it, for example, I have these membranes that I want to segment, right? And when people annotate them, they are typically not very careful. So they might end up a pixel beside the membrane. But I'm just looking for the maximum filter response then in a 2x2 neighborhood. So if it's just 1 beside the membrane, I'm still saved by this max pooling. You can also think in terms of these 3s here. This is a 3. If I just shift this 3 by 1 pixel to the right, it's still a 3, right? The label is still the same. And my filter here would have had the same response after the max pooling, because this maximum response to this filter would just have been shifted by 1 pixel. And because I'm pooling over a 2x2 neighborhood, I'm still capturing the same maximum. And we actually do this again. So now we have 4 feature maps, which then became 4 smaller feature maps. So from 1 larger image patch, I got 4, but smaller patches. And now you do the same thing all over again. So this was the first stage that looked for edges, for example. Now comes the second layer, again feature maps, right? And now I'm using these as input. And I'm doing the convolution for them, so I get even more smaller ones. And you do the max pooling again. And now what you do is now comes actually this flattening again. You take all these small feature maps, You just put them into one long vector and feed everything into a multi-layer perceptron here at the end. So convolutional neural networks are a small multi-layer perceptron with all this convolutional apparatus underneath. And these are used for image processing because this translation variance is very neat, and these smaller patches actually are also designed after the visual cortex. We have these small receptive fields in our brain. So, and the shifting of the convolutional kernel, you could have a fully connected network, a gigantically larger one that has the same power as the convolutional network, would have millions of more of degrees of freedom, because in the convolutional network, those weights are tied, because you're using the same kernel here. These are tied weights. You're using the same kernel going over the image. And this makes optimization easier, as in the autoencoder. So I've already said we're looking for things that make our optimization easier, because it's really, really hard. That is the bad news with the deep learning methods. They're cool, they work, it's extremely rewarding when they work. And most of the time it's just a when. It's just a matter of fiddling around with the parameters. Nevertheless, deep learning community has this term of grad student descent, because every graduate student gets one parameter setting that actually works, and then the next graduate student finds one parameter setting that works a bit better. Because there are so many parameters. If you think about it, it starts with the network architecture, right? Do neural network and random forest. I said random forest, or even support vector machine. You have the choice of your kernel, the kernel parameter, and the C. You're happy. Now neural network. Convolutional or not, okay, I can decide that based on the application. I need to know how many layers, how large should the layers be, how large should my input be, and then that was only the network architecture. Now comes the whole optimization apparatus. Those are trained with stochastic gradient descent. This needs a learning rate. You need a momentum parameter. You need the initialization for your W's in the beginning that you need to think a bit about. So there are all these tons of parameters. We need to know what they are for and what are sensible values that you could choose from. And then you need to find those that work best for your application. So this can be a quite slow process, because then once you have figured out one parameter setting, you hit go and you have to wait several hours before you get feedback whether that parameter setting actually was sensible. So this whole process needs a lot of time. And this is also why I highly recommend GPU processing for these. So this is this idea how they are trained. Just to give you, it's only this one video slide to give you an idea. So this is this energy landscape. You can see the dot is coming in, and it's taking steps, and it's trying to find the minimum here. And it does that by perceiving this as a valley, and the gradient shows you the direction of steepest descent. And the learning rate is kind of your step size with which you go down the hill. Now, if you make that learning rate too large, you're going to jump over your minimum. You're going to miss it. So if you make it very small, you might go all the way down, but you're actually going to take a long, long time to get there. So there's always this trade-off. So we said computer got faster, data got bigger, and its initializations got better. That is the next thing that changed in 2006. I said you need to think about the initialization of your W's. I already said typically they're done randomly. They are done randomly nowadays again, but 6 years ago they were not. And this is what gave them the breakthrough again of the deep learning methods, one of the big things that changed. What people did was unsupervised pre-training. They basically used this autoencoder that we discussed in terms for the Google Brain that was trained on unlabeled data. They used that to learn sensible features, and then they fine-tuned this with labeled data. So you can see the arrows here. This is just an experiment. I actually think this is MNIST data. I'm not entirely sure. But this is the same experiment, same network architecture. This is the number of layers, same optimization routine. This is just started with a random initialization, and this is done with this unsupervised pre-training. And you can see the test classification error really went down. So people were really excited when they tried this first. And they did these visualizations as well. So these are tracings, basically, of neural networks during training. So this is where they all started, and you train them, and then they end up somewhere in the space. So this is a two-layer architecture. This is with pre-training, and this is without. We can see two really distinct clusters. So they really converge to different solutions, just because people found a way to initialize them better. So how does it work? What you do is, you want a multi-layer perceptron, like this one here, where you have input, right, weights, hidden layer 1, weights, hidden layer 2, output, phase, yes or no. So you need to somehow initialize this W1 and W2. And I said one choice is just choose them randomly. That can or cannot work. What people did then was they used this autoencoder trick. That works without labels. So you can do, if you do face classification afterwards, you can go to YouTube. Doesn't even matter that much that there are other images in there as well. Of course, you would probably prefer to have face images, so maybe go to Facebook, because people maybe show more faces on Facebook than cats. So you have your input, and you train an autoencoder to reproduce the input. But what you do then is you throw away this layer here, right? Normally the autoencoder is just this, right? This was on top here before. This was the autoencoder, input, reconstruct, output. So all that this drawing here does is this autoencoder output is now down here. Now we're throwing this part away and instead train another autoencoder that reconstructs the activation of the hidden ones to be themselves again. Does that make sense? So I have now a hidden, how much do my neurons fire, right? The activation of the hiddens here. So I have an image patch, I put it in, I get my activation of the hiddens depending on W1. And now I train an autoencoder again that has some hidden layer, and the output should be the same as the activation of my hiddens. It's the same idea, just one layer up as before. So instead of reconstructing my image patch, I'm reconstructing the activation of the hidden units. And then I throw this guy away again and just put a logistic regression on top here. And I have a multi-layer perceptron now where W1 and W2 are not initialized randomly. Those guys there have already a notion of this cat and human face in the data. This is what people did for pre-training. And that boosted the results a lot. And then people got so excited about these methods that they actually started to label more and more and more. And nowadays, typically, the training sets are so large that you don't even need to use this trick anymore. But if your training set is smaller, but you can have access to a big set of unlabeled data, this is still the most useful trick you can do. Another trick that emerged was dropout. Dropout is a very simple idea also. As I said, a lot of things that worked really, really well in deep learning were these single insight ideas that were genius because they were so simple. So what Hinton does is he randomly masks out units. This is our normal multi-layer perceptron. And now, just with a chance of, I think, 0.2, and here even with 0.5, I mask units. I basically throw them away just for this iteration. So I'm computing the input, masking out this pixel, go up and say face yes or no. So then the feedback signal that all these other units get to update, right, this feedback signal will not regard these guys because they were masked out. So during this training iteration, I'm only training the ones here that don't have crosses on them. And then in the next iteration, you randomly choose different units to mask. And what he claims what this inherently does is it's averaging over all these different models. You have one big network, but by masking those units randomly, what you're simulating is actually a whole ensemble of networks of different size that are trained together somehow. But really the notion is to induce this element of randomness, like we did in the random forest. So this was a really cool idea. This does slow down training even more, but it allows you to train larger architectures on smaller data sets. So it really helps with the overfitting part of the neural networks. So then one last architecture, which I'm only going to go over very briefly because it's really different than the multilayer perceptrons and the convolutional networks, are recurrent neural networks. And the reason I want you to know about them is because they are for sequence data. And a lot of people are interested in time or whatever sequences. So a sequence is different because if I ask you to complete the sentence, if I only give you the dots, you can come up with whatever you want, right? If I say are cats black? Are you at home, right? There are still a lot of ways to complete the sentence. If I ask you, how are you, right? So when we have more context in the sequence, we get more and more sure about how we would complete the sentence. Context is important, again, in time sequences, but it's a bit different than in image processing. So you can train these recurrent neural networks to predict one character at a time. So you feed one text in, and you ask them, what is the next letter, and the next, and the next, and the next. It's actually cute. I've linked you an example where a guy trained this on Shakespeare data, and the network is starting to speak Shakespeare style, and he does it on Wikipedia, and really you can see the language is closer to Wikipedia. This is a recurrent network that came out of Hinton's lab, and Hinton is a very funny British humor guy, and he actually did ask the question that Google Brain didn't dare ask and found a cat instead, so he asked for the meaning of life, and this is what the network computed. So he gave the network the meaning of life is, and then they let the network generate one letter at a time. And you can see the meaning of life is bound to tradition of the ancient human reproduction. There we go. Go and multiply. So, and he claims that, I think he said that they ran this 10 times. So they ran 10 different sequences and then took the one that they liked the most. Okay, and what is the big difference here? The difference actually looks very, very small. It's a minor, minor thing. It's this. This is what transforms a multilayer perceptron into a recurrent neural network. So it's just not that much, right? It's like a feedback loop here. That feedback loop makes them really, really powerful, incredibly hard to train, because it enables them to have an internal state. What we have here is you have the input, you have the hidden layers, and then we just had the output before, and now we're feeding this output back into the hidden layer, which means the next time we have an input here, it's not only influenced by the input, but also by the output it produced before. That's the whole idea. So if we feed something like the word hello into this network, so it sees an H, an E, an L, this is the input layer here. This is how the different letters are represented. So I would really encourage you to look at this example. This is the guy who also did the Shakespeare and Wikipedia example. So H-E-L-L, and you can see up here, this is the letter it would predict, the highest one, without looking for signs here. The highest value here wins. So here's the E here, right? This is how the E was encoded with the 1 at the second place. So no, that's not true. It can't be the highest value. I'm still puzzled why this -1 is in there. But the real thing to notice is these guys change after seeing the second L. Although it gets 2 times the same input after seeing some other input in the past, here are 2 L's, right? And because this network has a memory of what it has seen before, the output changes and what it predicts next. So that is this power of this internal state. So these guys really rock for language processing and things like that. But I didn't want to just say deep learning is so cool and it works. It's hard to train, but after that, everything is going to be pink and fluffy. There's a very interesting paper called The Intriguing Properties of Neural Networks. So all this hype started, and people were like, yeah, this is what we should be doing. And then these guys took a network trained to identify objects, or scenes, I believe. No, scenes, objects. And then they looked how much they need to change this image to make it misclassified. So on the left, you have the image that is correctly classified. So the network would say school bus. On the right side, you have an image that doesn't look like a school bus at all for the network. And in the middle here, emphasized with a factor of 10, I believe, is the noise that they added to the image. That's weird, right? That looks quite disappointing. Like, after all that I said, CSAIL can put their stuff online, everything works so great. Now these guys look nearly the same, and the network totally screws up. So what did they do to find these? If we go back to our image. And I actually found it a bit unfair that they said these are intriguing properties of neural networks, because this is going to happen. You can do this with other classifiers as well. They're just not as hyped as the neural networks. So what happens is you have all your different examples of doggies here and of cats here. And it's a bit more complicated, right? Because there are tons of classes in this database, and you have all these images. But all what they did is they generated just enough noise to put this sample over the edge, right? This is what makes the school bus just not a school bus anymore. And now, this decision surface, there is one thing where it actually is the fault more of the deep learning methods. This is what a support vector machine would give you, right? Max margin. There is nothing when training deep neural networks that has this max margin property, right? When we talked about the perceptron is happy if the mistakes are low. So for a perceptron, this here is a completely acceptable decision boundary, right? And now it actually doesn't take much to push something over the edge. So just a paper I recommend reading. It was still quite interesting that they did this, and they got quite some recognition for it. So one interesting, I'm just going to go over this quickly. One interesting question was actually on Piazza, and I thought this is a really cool idea. I forgot the name. I'm really sorry. Somebody asked for libraries for deep learning, because now I've told you how it works. You should have enough understanding now to go home and train your first network. But the question is how, right? So here are some of the more popular libraries. There are tons of others out there. Theano is the one I use the most, actually exclusively. I really like it. Torch is another framework. Caffe and TensorFlow is the one from Google that just recently came out. I believe Caffe is from Berkeley. Torch is not really from Jan LeCun. I thought it's from Jan LeCun because it's like very convolutional network based, but it's not really from him, but 4 of the people, or 3 out of the 4 people who maintain it are from his group. So it has tight bounds to Jan LeCun. And Theano, one of the guys, James Bergstra, actually was here in David Cox's lab. So I'm going to start with Theano. As I said, full disclosure, this is my favorite. It's completely Python interface, and it has transparent GPU integration. What that means is you do not need to take CS205 to program this. You do not even need to know CUDA. All you need, CUDA is the NVIDIA programming language for their GPUs. Because all you need to use is this Theano library, and then there is one flag that you set, and this flag just decides whether that code is executed on the CPU or on the GPU. But that is actually also something the other libraries have that I have here. All of these should enable you to do GPU computation without really knowing about it. So it also has symbolical graphs. What that means is Theano builds up a graph on a variable. We said all of these networks are really just matrix multiplications. Theano is not going to compute these right away. It has this lazy evaluation idea that we also had kind of in Spark. You have your input, right? And I just specify, multiply this with this weight matrix, add this bias, do this nonlinearity, and then go on, right? And I stack all these functions on top of each other. And then at some point, I press evaluation, and only then this whole graph is unraveled. The reason that is nice is It can do internal optimization. Just if I would, I don't know, multiply by a number and in principle divide by that same number later on, it could get rid of that computation. So under the hood, it's very clever and optimizing for you. It also does auto-gradient. Also, this is something that's just very important. Deep learning, the stochastic gradient descent, that valley that you're looking for, to have that direction to go to, you need the gradient. Computing the gradient is not that hard. You can do it. I've done it like step by step on paper. You're going to waste some sheets, and then you know how it's done. But it's nice if you don't have to do it, and Theano does it for you. And what I like about Theano might be the reason you don't like it. It's very low level. You actually plug your networks together. You can see what the single layers do, and you can also reprogram those very easily. Like if you want a different architecture that is not standard, if you actually are interested in trying out new ideas, then this library is low level enough that this is very easy, and high level enough that it can be done very fast. If you want higher level on top, there is PyLearn2. This is very research-based, so this dropout network, for example, or if you want to see a state-of-the-art classification of MNIST, PyLearn2 has all these configuration files. You just specify your network architecture, you push a button, say go, and it trains your neural network for you. And these Keras, Lasagna, blocks, these are also libraries that build on top of Theano. Theano's optimization works so well and is so nice and fast, but the interface, you really need to know what you're doing. So people build these high-level libraries on top of Theano. Then there is Torch. The only thing I do not like about Torch is that it's Lua-based, no Python. That's also the only reason I'm not using it. Ray Jones is using it, and he likes it very much, except for Lua being 1-based and not 0-based like Python. It has very fast convolutions. As I said, it comes kind of out of the lab of Jan LeCun, who's the guy behind the convolutional networks. He was the one who developed them in the 80s and stayed faithful, and now actually had his big breakthrough. This is something I admire about all the big names in deep learning. They've been with these methods since the 80s, and they believed in them, and they didn't work, and nobody believed in their methods. There were these tiny group of like 5, 6 people, and now they're hired by Facebook and Microsoft, and everybody is like in awe of their genius. So this is also the library that is actually used by this DeepMind, Facebook, IBM. They're a lot into Torch. And this is layer-based instead of graph-based. I said Theano has this computational graph that then gets computed. In Torch, you actually have the single layers of your network. So if you want to implement a new one, you would have to build a new class. Café is C++ based, doesn't have a symbol. It's a higher abstraction than Theano. Torch might be a good thing for an introduction to deep learning, because it also has this model zoo. Because they're highly standardized and they're more high level, they actually have a website, a library, where you can download pre-trained models. So you don't have to wait 3 days to do a classification of faces, for example. And then there's TensorFlow, which actually was the reason this question popped up, I believe, because it was like, okay, how does TensorFlow relate to the other libraries out there? The answer is, I don't know that much yet. I haven't looked really into it, because one of the first things I read was they still have performance issues. So at the moment, TensorFlow is still slower and more memory intensive than the other libraries. So here I linked you for some benchmarks here. And it looked to me like it's a really cool idea. It's basically a very clean version of Theano. This is what it looked like to me. But under the hood, they still need some work. Yeah, I'm not going to go through these tips and tricks now. I'm just going to tell you that at the end of my presentation, which I'm going to put online, there are some tips and tricks if you want to do deep learning, what to look into for parameter choices, for training this, what are good learning rates that you can choose, how to visualize your layers during training to see what is going on. Because I'm going to close here.